This video will discuss the final FRQ from the 2024 AP Calc AB free response set. Number 6 is a non-calculator question where they talk about the functions f and g. They do present you with the equations for both f and g, and they give us the graph. So part A says we're going to let region R be bounded by the graphs of f and g from the x of 0 to the x of 2 as shown in the graph. Right, but do not evaluate an integral expression that gives the area of the region R. So I always have explained area and volume problems in 3 steps. Slice, approximate something relative to that slice, and then integrate to add together infinitely many of those slices, areas, volumes, whatever sort of calculation you're trying to do. So with the slicing step, we need to decide, do we want vertical slices or horizontal slices? It makes sense to go with vertical slices here, and the reason for that, every single vertical slice, the top boundary, is going to be on this graph of f of x, and the bottom boundary for every vertical slice that we could draw is going to be on the graph of g of x. So I've got a vertical slice. The width of that vertical slice is a tiny, tiny change in x, and then the height of that vertical slice has to be positive. I need to take the top y value minus the bottom y value to make that height dimension positive. The top y value, as we indicated a few seconds ago, is y equals f of x. The bottom y value is y equals g of x. The area approximately for that one slice, if we pretend it's a rectangle, is going to be height times width. That'll just be the area of one slice. I want to add together infinitely many of those slices' areas. An integral adds together infinitely many products of expressions like this. So when I integrate this expression in its limiting form, the delta x is going to transition to a dx. And the last step would be to make sure you attach limits of integration. What x's do all slices that you could have drawn in region R range between? 0 on the left edge and 2 on the right edge. Part B says region S is in the coordinate plane, bounded by the graph of G and the x-axis on the interval from 2 to 5, and that's also shown in the graph. Region S is the base of a solid. For this solid, at each x, the cross-section perpendicular to the x-axis is a rectangle with height equal to half its base in the region R. So the base of the rectangle sits in the region R. Find the volume of the solid. Show the work that leads to your answer. So this is not setup only. This is find the volume. So we need to set up the integral, and we need to evaluate the integral. I would have much preferred to evaluate the integral that we set up back in part A, but we didn't get so lucky. So how do we go about this? We don't get to decide how we're going to slice. They force us into a certain orientation for our slice. Our slice has to be perpendicular to the x-axis. So we've got a vertical slice that is perpendicular to the x-axis, and I've got a solid that's sitting on this region, and if I take a thin sliver, a cross-section of the region from right here, what I'm guaranteed to be looking at if I cut that cross-section out and lay it out flat is I'm guaranteed to be looking at a rectangular face. Now it tells me that the base is in the region R. So you'll notice that I shaded this slice in, I shaded this edge of my rectangular cross-section in. This cross-section has to be able to be replaced back down between the two bigger portions of the solid from where it was removed. So there's a direct correspondence between this in the coordinate plane and this edge on our cross-section. That allows me to recognize that this dimension, the base of the rectangle, is going to be given by top y minus bottom y, g of x minus 0. The tiny little bit of thickness that this cross-section has is going to be given by the tiny little bit of width that this two-dimensional slice has, which is delta x. And then it tells me that the other dimension of the rectangle, I know it says it's the height, and it might seem a little bit weird for me to have labeled this dimension across the bottom as 1/2 of this dimension, but I just wanted to make sure there was a direct correspondence between the way that my cross-section was oriented within this diagram and how it had to fit back into the coordinate plane. We get one dimension from the rectangle from the coordinate plane. The other dimension from the rectangle is just half of the one we get from the coordinate plane. So what is the approximate volume of this cross-section? Well, it's going to be g of x times 1/2 g of x times delta x. We want to add together infinitely many of those cross sections volumes, so I'm going to let the integral do that work. So I'm going to integrate 1/2 times g of x, or g of x squared. My slices that I could have drawn are going to range from an x of 2 on the low end to an x of 5 on the right end. I need to find the value of this. So I am going to replace g of x with what they tell me g of x is equal to, so x squared minus 2x. I can't ever distribute an exponent. I am going to have to FOIL that expression out. I don't have a product rule for integration, so that is going to be a step that's necessary to do. So after you FOIL this out, you should end up with this result. I take the antiderivative of that, which isn't too bad. I then, using fundamental theorem of calculus, put in the upper limit, the lower limit, and I take a difference. The bottom line on this screen would receive full credit on the AP exam. I am stunned that they put this problem on the non-calculator section of the exam, because if you were to not realize that you can stop your work right here, you spend about 10 minutes doing arithmetic, wasting a ton of time, taking on a ton of risk to simplify this thing to 414 fifths without a calculator. Hopefully most students taking the exam know that this is not necessary to do. It wastes a ton of time. It introduces a lot of risk. I'm sure when the scoring guidelines come out, this is the answer that will be posted. Never have I seen such a lengthy sequence of simplifying steps, not required to do, but available to do for students that didn't realize that they did not need to be done. So leave your answer back here. Do not do this. Last part of this says, write but do not evaluate an integral expression that gives the volume of the solid generated when region S, as described in part B, is rotated about the horizontal line y equals 20. So if I draw my horizontal line y equals 20, think about rotating region S about this horizontal line. I need to recognize that because of this gap that exists between the top of the slice that I've drawn and the axis of rotation, I'm going to generate a washer when this slice gets rotated about y equals 20. With a washer, there are two significant dimensions to try to identify from out of the coordinate plane. There's an outside radius. The outside radius is going to go from the axis of rotation to the far edge of the slice. This dimension in the coordinate plane is a vertical dimension that has to be positive. To get it into place, we take the top y, which is at the axis of rotation, subtract the bottom y, which is at the bottom of the slice, which is always going to be a y of 0, no matter where in region S I draw my slice. My inside radius exists because of the gap between the axis of rotation and the nearer edge of the slice that's rotating about it. So in the coordinate plane, this would be my inside radius. Again, a vertical dimension that has to be positive. So I'm going to take the top y, which is a y value of 20. I'm going to subtract the bottom y. Now the bottom y is not 6 or 7 or whatever you're looking at over here if you're working directly across to the y-axis. That value, that bottom y, is going to change depending on where I choose to draw that slice. That bottom y is the y value from this graph, which is y equals g of x. So 20 minus g of x would be my inside radius. The area of the face of the washer is going to be pi times the outer radius squared minus pi times the inner radius squared, right? Outside circle's area minus inside circle's area. The approximate volume of this one washer is going to be that expression for the area of the face times the thickness, and the thickness of the washer is due to the tiny little bit of width, delta x, that the two-dimensional slice has within the coordinate plane. I want to add together infinitely many of these washers' volumes, so I'm going to let the integral do the rest of the work. I'm going to add together infinitely many by integrating that exact expression. Once again, in its limiting form, the delta x turns into dx. And what x's do my slices range between in the region S? 2 on the left edge and 5 on the right edge. Luckily enough, in this part, we do get write but do not evaluate. Once again, we are done right there.